Hello and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving the over 100,000 computing professionals and students who are ACM members. I'm Rajiv Thakur, Deputy Director of the Mathematics and Computer Science Division at Argonne National Lab, where I'm also a Senior Computer Scientist. I'm also a Senior Fellow in the Computation Institute at the University of Chicago and an Adjunct Professor in the Department of Electrical Engineering and Computer Science at Northwestern University. My ACM volunteer activity includes serving as an elected member at large on the Executive Committee of ACM SIG HPC. You can find more about me in the BIOS window on your screen. For those of you who may be unfamiliar with ACM or what it has to offer, ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. You can see some of the highlights on your screen. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. The slides will advance automatically throughout the event. On the bottom panel, you'll find a number of widgets and resources. If you are experiencing problems with the slides or audio, press the F5 key in Windows, Command+R if you are on a Mac, or refresh your browser on a mobile device, or close and relaunch the presentation. To control volume, adjust the master volume on your computer. At the end of your presentation, we will have time for questions. Please type your question into the Q&A box at any time and click on the Submit button. This session is being recorded and will be archived. You will receive an automatic email notification when it is available, and check learning.acm.org in a few days for updates. You can also use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag #ACMWebinarScaling. We'll be watching for your tweets. Today's presentation is on extreme scaling and performance across diverse architectures by Salman Habib. Salman holds a joint appointment as Senior Scientist in the High Energy Physics and Mathematics and Computer Science divisions at Argonne National Lab. He's also a senior member of the Kavli Institute for Cosmological Physics and a senior fellow at the Computation Institute at the University of Chicago. He received his PhD in physics from the University of Maryland in 1988. After 20 years at Los Alamos National Lab, he moved to Argonne in 2011. His research has covered a wide range of interests, including cosmology, astrophysics, accelerator physics, condensed matter physics, atomic and quantum optics, and particle physics. For the last 2.5 decades, Salman has been very interested in the intelligent application of parallel supercomputers to attacking physics problems, leading to algorithm and code development in a variety of fields and on a variety of platforms. Salman, we look forward to your presentation here today, and you can go ahead now.
Okay, thanks, Rajiv. So I will just start with the first slide, which has the title slide, Extreme Scaling and Performance Across Diverse Architectures. And obviously, a large project like this that I'm talking about, even though the team is relatively compact, has involved many contributions from lots of people. So I want to acknowledge them all in the first slide. And we've also had support from various agencies and organizations who are also acknowledged on the first slide. So one of the important things I would like to get across here is that a lot of the work that I'm going to be talking about does not require, intense amount of detailed work, and it's important to just have some basic ideas at the back of your mind when you are implementing large-scale computing methods and looking for applications. So let's get started with the actual slide where the meat of the talk starts, which are the computing needs for science. So obviously, science has a wide variety of computing, right? I mean, you can do very interesting stuff right on your laptop. You don't necessarily need to do large-scale computing. But there are many communities that use large-scale computational resources for a variety of tasks. And these communities are, biology, the people who use light sources, climate, obviously, and earth sciences, high-energy physics, and materials modeling. So all of these fields tend to use computing in different ways. You can do traditional supercomputing. You can do large-scale data-intensive computing. Sometimes there are many sensors all over the world, and they're gathering information. And you have to combine all that information and learn stuff from it, so that's more data-intensive. So in any case, there are a wide variety of use cases of large-scale computing. And what is interesting today is that in the past, these cases were often isolated, meaning the people who did supercomputing didn't really need to look at the data. A lot of the people using data were just trying to learn some phenomenological facts. They didn't necessarily need to do a lot of supercomputing on top of that. But what I think is characterizing the next scale or the next generation of applications is the fact that all of these different computing threads are coming together. So traditional supercomputing is meeting data-intensive applications, and so on and so forth. So when you think about extreme scale computing, you should remember that there's going to be an overall balance of compute and I/O and storage and networking and simulation and analysis, and it's the big picture of the extreme scale workflow that you have to keep in mind. So if you have a task where someone says, try and optimize such and such, you should not think instantly like, okay, I'm going to work on this particular optimization problem right away. You should take a step back and say, what's the global context in which this particular piece of computing fits? And only then should you start thinking about how to optimize it, because maybe the right answer is not to optimize the chunk of code, but to actually change its place within the ecosystem of computing. Okay, so with that, let's go on to the next slide. And now I think I already introduced the different flavors of computing, but I think it's important for people to just keep three different flavors in mind. So the first of them, which is traditional high-performance computing, where you basically solve partial differential equations or you run n-body codes like the one I'll be talking about. So these systems are by now all parallel systems with an extremely fast network, or supposedly extremely fast network. They're designed to run tightly coupled jobs. So in other words, each processing unit is talking to the other processing units. And typically you want a high-performance parallel file system to go along with this machine, because the RAM, there's a large amount of RAM, and you want the data to go in and out of the machine as fast as possible. So typically you want to be able to move the data in and out of the machine if you're running a very large code in, let's say, 10 minutes or something of that nature. And the general way you use these machines is through batch processing. So you submit a code or you submit a job, and then you wait. And when the machine has space, it lets your job in, it runs the job, which could take hours, and out comes the data. And then maybe you want to resubmit. So a simulation campaign on such a system can easily take weeks or months. And sometimes it can be much shorter, but that's typical. Then another type of computing is data-intensive computing, which is essentially analytics. So now you have, let's say, collected a fair amount of data, which could come from an experiment, or the data could come from a simulation performed by a high-performance computer. And you need to do a lot of analysis on it. And you want to do what I would call interactive analysis, meaning you want to ask a quick question and you want the answer to come back saying yes or no, or you want an answer accurate to about 10%. You don't need to know the details, but that is going to be something that will help you ask the next question. So these are important aspects for data analytics. So these systems typically have a system-level storage model. They're typically designed for interactive processing. And currently, they're not as large as the high-performance computers, but they're getting to the point where they will be, very important systems of the future. The third and final system I just want to mention is high-throughput computing, which is basically what also people call PC farms. And so you have a large number of computers, and they're distributed, and the slow network is essentially could be the internet. And they're designed to run very loosely coupled jobs. So you start a large stream of jobs. Some will finish, some won't even finish. And then in the end, you collect the information from them. The ones that failed, you restart. So you have a very distributed data model in this particular case. And this, again, is a batch processing system. You're not going to get anything interactive out of the system. And again, the analyses that you might be running may go on for months, and then the answer will eventually appear. But these are all, in principle, very large-scale computing systems, and where you can go to millions of cores, for example, in any one of these. Okay, so in this particular talk, I'll be focusing on the high-performance computing end of things. So that takes us to the next slide. So before you actually start asking, what I should be doing in terms of, as I was saying again about performance, it's an actually interesting question as to when you might want to use a high-performance computer, and when and how and once you're using the system, whether you should really go for extreme performance and extreme scalability. So the motivation for large high-performance computing campaigns are not that many. I mean, basically, you want to have quantitative predictions for complex nonlinear systems. That's typical. It's something that you know the equations for, but you simply cannot solve them with a pencil and paper. The other question is that you want to expose physical mechanisms. For example, you have a very complicated system. You want to know why is it doing certain things. For instance, you run a code and you get a particular answer, but knowing the answer is only part of the big problem. What you really want to expose is the physical mechanism by which that answer appeared. So that is also something you can use computers for, and that's actually, in my view, one of the most important ways of using a supercomputer. It's not simply to generate numbers, but to generate insights, as many people have said. Finally, not finally, but number 3, there are system scale simulations. So in effect, before you build, say, something very, very large and spend, say, hundreds of millions of dollars, you may want to actually do a system scale simulation and see whether some essential aspects of the design of, let us say, an accelerator or an industrial plant or something like that, where there are some intrinsic flaws, where there are some instabilities, was everything done right? And obviously, these are impossible experiments. Climate is a perfectly good example of this. We're not going to recreate a planet just to see how climate works. We're actually going to run a simulation. So, and then finally, there are these data-intensive tasks that I had mentioned earlier, large-scale inverse problems, where you may have a flood of data, and you may have a model, and you want to understand what the parameters of the model are given this flood of data. This is typically done by Markov chain Monte Carlo methods, where you run the forward model, that is to say, the model that you have in mind, but with different parameters over and over again, and essentially compare with the data that you have. So here again, if you have a complicated model, you might need to run a very large number of these model runs, maybe hundreds of thousands or some cases millions, and so you need high throughput. So one reason why a computational cosmology example, like the one I'll be discussing later, is a good example for high-performance computing is the fact that all of these 4 things that I mentioned come up in computational cosmology. Now, the role of scalability and performance in this is kind of interesting because just because you need a few very large simulations doesn't necessarily mean that you need to go overboard on performance, right? Because it could be that you're happy with 5% of peak because you only need to run 1 simulation a year. But if you need to run, let us say, 10, 20, 30, 100, then you might worry about getting another factor of 10 and speeding things up to about 50%. So there are various reasons why you might want to increase performance, why you might want to scale. I won't go through all of them. They're on this slide. And so let's move on to the next slide. And here, so everything I've said so far is kind of universally true, right? I mean, no matter what time or what era you're in, all of that is more or less true of computing. However, now, starting in 2004 and in this current era, we see a real problem, which is the hardware revolution. And of course, many of you understand this very well, but I will simply repeat it. So starting in 2004, as you can see from these graphs from Coggy and Resnick's review, something very interesting happened. The clock rate stalled, and also other things changed, but I just use these 2 figures. One is to show that the clock rate on processors basically kept going up, and then it stalled. And the other thing that's interesting in this figure is, I'll come back to that later, is the fact that the memory on a machine is going down as a function of the flops that the machine has. So these are 2, if you're interested in supercomputing, these are 2 very important facts. And essentially this is coming from the fact that power is expensive. You have to pay for it. And so you can't just keep building a machine with more and more, power. And at the same time, memory is expensive. And so if you have a lot of compute, you need a lot of memory. Unfortunately, you will not be able to afford memory. So let us say that so what is our current situation? We want to have a 30x performance gain in supercomputers by 2020, or say in the early 2020s. Machines right now are running at tens of petaflop, and we expect them to be in the hundreds of petaflop by 2018, 2019, several hundreds, and then move over to the exascale in the early 2020s. It is not unreasonable to say that a power budget of 10 to 20 megawatts for a large system, that's what the power budget should be. Anything more than that will get very expensive. The important thing to keep in mind is that power per socket is roughly constant. Now, given these constraints, the only way out to get performance is to increase the number of cores. And increasing the number of cores basically means that now you have a very large level of concurrency to deal with, and this is what is frightening programmers. None of the choices that are being presented to a scientist or a programmer are particularly nice. I mean, we would much prefer to have more powerful cores, right, and less of them. But that's what it is. So now if you have a whole bunch of simpler cores, clearly microarchitecture gains of the past have to be sacrificed. And you have to think in new ways. You have to accelerate specific tasks. You have to have a more restrictive memory access structure. So you have to look at SIMD methods and SIMT as in GPUs. And finally, there's one very important thing is that the machine balance is changing. And that's an example of this memory to flops figure on the bottom right. And the same thing is happening with communication bandwidth versus flops. You have a limited amount of communication bandwidth, even though you have a lot of compute flops. And all of these metrics are going in the wrong direction, meaning the machines are becoming more and more unbalanced, which means that a lot of code refactoring is going to happen in the future, right? So this is what this slide was supposed to convey. So now let's move on. So what exactly, so right now I talked a little bit about the hardware at the lower level, and then we have to come up and say what is happening to supercomputing systems. So first of all, high performance computing has changed quite a bit already. For example, in the 1990s, basically the desired machine was what was called a balanced machine, meaning you balanced your memory to your flops, you balanced your network to your flops. And so there were a bunch of metrics that you used, various ratios, and they were all supposed to be nominally of order 1, right? That was a desiderata, to build a balanced machine. However, the fact that the power constraint is so important means that we can no longer build a balanced machine. And it's not just power, it's also, as I said, the fact that memory is expensive, the fact that networks are also very expensive. So these metrics that used to be of order 1 or 0.1 have now all changed. And on the same system, if you go ahead and ask what these metrics are on the same supercomputer, they range from 0.1 to 0.001, which means that the machines are actually quite out of balance, which means that programming for them is really quite difficult. So I already mentioned this business about memory, but why is this important for scientific computing? So it used to be as the machines got bigger, and that is to say faster, they also got bigger, meaning they had more RAM. So many applications, including ones that I'm interested in, dealt very nicely with this because they had a fixed relative problem size. What it meant was that the amount of the task related to a single processor basically didn't change. So as you produce for me a faster processor with the same amount of memory and more of these processors, I was perfectly happy, okay? But that is now ending. And so the first challenge we have to face in scientific computing on supercomputers is that now that the memory is fixed, we have a fixed absolute problem size. Although the memory is not quite fixed, but it's going very slowly. So the absolute problem size is more or less fixed. But now the concurrency is increasing. So we have a situation of what's called strong scaling, meaning that the absolute problem size is fixed and the number of processing units is increasing. Now this is much harder to deal with than weak scaling, since the metric really is now performance and not simply scaling. So it used to be in the past, as long as your code more or less worked and you could keep the communication costs under control, you could weak scale. But that is not going to be true anymore. So much harder in the future. The other thing that's much harder is that machine models are more complicated. The machines are not as simple as they used to be, which is basically one processor and a network, multiple processors and a network. Now you have a multiple hierarchies of compute, memory, and network. And that means that you have to think hard about how you're actually going to break down, what your code does. Secondly, in order to really do well in the strong scaling regime, your codes must add more physics because you need more computation now. And adding more physics is obviously going to make everything more complicated. You have more multi-scale, more multi-physics tasks. So the point I'm trying to make is that the computational problems are going to be much harder, and putting them on the machines is going to be much harder. The other difficulty that enters here finally is the fact that the architecture, there's not a single uniform architecture that's the target architecture, right? There are a whole bunch of different architecture choices. There's many core, there's going to be extreme multi-core, there's going to be low power chips, there's going to be GPUs, there's going to be accelerated systems. So if you focus all your effort on one kind of architecture, you may find that, oops, your code is totally unsuited to another kind of architecture. So the portability issue is extremely important. So moving on from there, we also have a sort of sociological problem, which is that given all of this, the final solutions must come from people. And this is actually made difficult because supercomputing or large-scale computing is often a niche activity. So most codes, in fact, are written and maintained by small teams. And they're already working close to the limits of their capability. Maybe students and postdocs have contributed to the code, professors in charge of controlling it in academia, and in labs, the teams can be bigger, but still there's a finite size of the team. And there are no free cycles usually available to team members to do new things. So all of these challenges hit them, it's going to be very difficult. At the same time, okay, then there are other kinds of codes like community codes, and the community codes are, involve many more people, but by definition are associated with a large inertia. It's not easy to change the standards and untangle lower-level pieces of code from the high-level organization and find the people that have the required expertise to help out, when required. So the point is that you have a timescale issue, meaning that the code teams who are writing codes either have no time, so anything they do will be very, very slow, or there's so many of them that, once again, timescales are slow. And this is a problem because the software timescales tend to be very long, 10 to 15 years. Whereas computing is right now changing on a few-year time scale. So this is a difficulty. Another problem that exists right now is the lack of a consistent programming model for scale-up, meaning you would like to be very easily run test code on your laptop and then say, oh, great, it works nicely, and now I can just upscale it and run it on a machine. And you would really like to be able to do that because as the number of architectures change, it would be nice if I could handle all of the simple stuff on my laptop or on local computing resource, and then very trivially send it to a big machine to run. But this, unfortunately, is not possible right now. So that's another big issue. So because of all of these things, in some fields, certainly, something like a crisis is approaching, or so people say, right? And I think this is something we have to confront in large-scale computing. So the question then is, well, what do we do about it? So first of all, I think I'm an optimist. I don't think that the situation is dire, but I don't think it's disastrous. So we will get beyond this, and we already have one example in our past history of doing this, which was the transition from vector supercomputers to massively parallel systems. And initially in many fields, there was this doom and gloom that, oh no, this will be disaster, we will not be able to do it. But in a few years, the transition did actually happen. So the important thing is that transitions will happen, but they need to be staged appropriately and needs to be managed appropriately because there's not enough manpower to entirely rewrite the code base. So for certain fields, for example, the code base is in the excess of something like 10 million lines of code. They're not going to instantly rewrite such a large code base. So there are two things that, though, you have to realize that even though the solution may be possible, it is very unlikely that there will be ready-made solutions. So people worry a lot about portability, and they're talking about ways, high-level languages and so forth. But history says that ready-made solutions will not exist. I mean, if you look at the past, that has rarely been the case. So therefore, the code teams will have to do a lot of things. And so the fundamental realization is that you have to do it for yourself. And, it's unlikely that a major solution will just pop out. So this being the case, we have to consider some of these high-performance computing myths that, especially this is true if you're a domain scientist, you're always told, don't worry, magic compiler will appear, problem will be solved, beautiful computing, beautiful programming model and language will appear, problem will be solved. There'll be special purpose hardware, it'll deal with your problem. None of this ever happens, right? So it's important to keep this in mind. The other interesting thing that could possibly happen, but it has not happened yet because supercomputing is not big enough to drive the vendors is co-design, which is to say that you tune the actual chip itself to the application. And that's not possible for most of us. Yes, it's certainly possible for some people who have enough funding, but not for most of us. And it is something that could happen in the future as chips become more flexible, but that's currently not the case. So in order to deal with today's reality, the code teams, that's basically an important message, that they must understand all levels of the system architecture, but it's extremely important not to be enslaved by the system architecture, meaning don't follow it all the way through, because if you do, your code is going to be written to a particular architecture, and then it'll be very hard to port to something else. It's important to have a good idea of the boundary conditions in the future, what may be available, what is going to be doable. So if you're going to design something now, you must think, I mean, this is all kind of trite, but you have to think about where the architectures might be going. Previously, in the 90s, you had a very good predictive view of what the architectures were going to do, and that's not the case right now. So we have to do a lot more defensive programming right now than we had to do in the past. One of the important things to keep in mind is, and I always say this, is that code ports, the idea of a code port, is ultimately a false notion given the architectural diversity. So the general idea is that domain scientists have written some code, and they hand it over to vendor experts and or supercomputing experts who quote unquote port the code to a machine. And my claim is that this is possible only under very limited circumstances, because things have gotten to the point where you may have to actually change the algorithmic structure of the code. You may actually have to change very fundamental things about how the code is written. And this is not something you can do by just throwing it over a wall. So you have to start thinking out of the box, and domain scientists and computer scientists and engineers must all work together. So this is something that was extremely important in the example that I'll be talking about. So the example I'm going to be talking about, so now I'm going to switch quite drastically. So sorry about this one equation that now appears. So this equation describes the evolution of the large-scale structure in the universe. And when I mean the large-scale structure of the universe, I mean the following. At very early times, the universe was basically very homogeneous as a hot ball of gas and radiation. And over time, as the universe expanded, literally as space was created, the temperature of the universe went down, and this gas of matter sort of coalesced into the galaxies, stars, planets, and so on. So the universe, as we can observe, is very, very large. To give you an idea, the observable universe is of the size of gigaparsecs. A parsec is 3.26 light years, and giga here is obviously billions. So you can see, so billions of light years. And the structure that when people talk about large-scale structure, they mean how galaxies are distributed in the universe. So typically, a galaxy size is, of the light of the galaxy, stars is about tens of kiloparsecs. And the separation between galaxies is of the order of a megaparsec. So if you want to know what the structure of the universe was on the scales of megaparsec, and keeping in mind that you can observe out to gigaparsecs, what is that equation? So that equation comes from general relativity, and with some approximations, it's something called the Vlasov-Poisson equation. And it's very, very similar to what's also used in plasma physics, except that it's, here you have gravity and there you have electromagnetism, but it's very similar. So it's a six-dimensional partial differential equation. And it has some very interesting properties in the sense that it has long-range interactions which cannot be shielded, which means that all scales matter, which means that when you're writing a code for this, not only are there small-scale interactions, there's also long-scale interactions. And the other thing is that what happens when you run this evolution forwards is that there's a gravitational instability. You can start with a very smooth initial condition, but a lot of structure is generated, right? Galaxies, planets, and so forth. And this is something called the Jeans instability. And this instability works at all scales. So whether you're on large scales or small scales, all scales, gravitational collapse happens. So there's extreme dynamic range when you're trying to solve this equation, and typically this equation is solved by n-body methods for technical reasons I won't go into right now. But I will tell you a little bit more about the scales in the next slide, just to give you an idea about how this is really an extreme scale computing problem. So and these are the only two slides where sort of the science enters. So if you have any science questions, please feel free to ask. So as I was saying earlier, the light in galaxies come from stars, And typically, when you see the luminous part of a galaxy, what you're not seeing is a large amount of dark mass, which the luminous part is inside of. And this dark mass, which is what we call dark matter, that typically extends to about hundreds of kiloparsecs. So if you're going to solve this equation that was on the previous slide, you need a force resolution, meaning you need to resolve in spatial scale something of order of a kiloparsec. But as I said, the entire box, which is what a survey might be able to observe, might be gigaparsecs, which means that the dynamic range is 1,000,000 to 1, right, in space. A similar calculation is easy to show that the largest object mass to lightest object mass that you want to have in your simulation is something like 10,000 to 1. So this means that you have a very difficult problem computing-wise because you want the spatial resolution everywhere. It's not like you can run an adaptive mesh refinement code and say it's only in one place that I need the resolution. You need this high resolution everywhere. And so if you actually go ahead and compute, the boundary conditions, meaning like I was saying earlier, right, you must have some idea what the computing boundary conditions are. So in this particular case, if you want to do a large cosmology simulation that effectively captures what an observational survey is going to see, you have to have a total memory in something like the petabyte class for the machine, and your performance should be of the order of 10 petaflops. And this will give you a wall clock of days to a week or maybe weeks in order to do one universe, right? Now you might say, well, if we only have one universe, so aren't you guys done after running one universe? And the answer is no, because we don't actually know the parameters that our particular universe has. So when we actually run a simulation, we need to compare with data that is taken from surveys, and that might require many, many simulations, hundreds of thousands or millions. So this was the point I was making earlier, that you have to do lots of simulations. The other interesting thing here is that we have now observations that are very, very detailed. So statistical quantities in the observations can be measured to of the order of 1%. And therefore, the simulation that we are doing must be accurate to fractions of 1%. So this means that you have to really, really understand, what your code is doing and be in full control of what's going on. So that sort of sets the scale for the class of problem that we have to solve. Now I will give you the story of the HACC code, which is a hybrid hardware accelerated cosmology code framework, and how it started. And this is a kind of an example of how to proceed based on all the preliminary stuff I told you, right? So when we were at Los Alamos, we actually faced the problem that most people are facing now about hardware change already in 2007. When Andy White, who was the head of computing at Los Alamos, sent me an email, which I still have. And the title of the email was, "What if you had a petaflop?" And honestly, at that point, it's like if you were to ask today is if you were to get a similar email and that said, "What if you had an exaflop?" Well, the first thing you say is, "This is great, give me that." but the next thing that follows is they tell you, yes, it is a petaflop. However, the machine architecture is going to be very messy. And so on this slide, you can see the architecture of Roadrunner, which was the first machine to break the petaflops barrier. And it was very similar to a modern accelerated architecture, right? I mean, except that instead of GPUs, it had the IBM cell. And then attached to that were optrons, and then the optrons talk to each other through an InfiniBand network. So the important point was that all the processing power was in the cells at 200 G-flop or single precision per cell. But the cells could not talk to each other directly. They had to go through to the AMDs. And then the optrons could talk to each other through the network, okay? So you can see that you have a problem. You have 200 G-flops of performance on the cells, but there's a PCI link to the optrons, which is only running at a gigabyte per second. And then the layer, which is the optron layer, only has around 50 teraflops, right? And that's the one that's talking to the switches. So the InfiniBand has the right network bandwidth to sort of be balanced with the 50 teraflop of optrons, but it's totally not balanced for the petaflop of the machine. So the machine was off balanced by a factor of about 50 to 100, which is very typical of what you see today, right? So the task was write a code that will scale across this machine and will run at high efficiency. So the first question that I had was, when faced with this, is it even possible? And the second question was, if it is possible and we do write such a code, what are we going to do with it when Roadrunner goes away? And for us, it was a very, very simple question because Roadrunner was meant for classified work. So it was only open for a few months when it could be used for open work, which meant that if you spend a year or two and wrote a code, and you had only a few months to run it on, you basically wasted your time. So it was pretty clear that whatever code we were writing must have a long-term future. Okay, so those are important things to keep in mind. So the architectural features of this machine are very similar to things I've already mentioned. So I won't bother you with that. So let's go on to the next slide, which talks a little bit more about HACC. So given that we had this problem of trying to figure out a code that should work and should be extendable to other machines, the important point I always say about these things is that you should first step back and think, in a global way. Try and think, what do I have to do in order to get this thing to work? So literally the answer for the code's overall structure was done in one afternoon on a weekend. Everything after that was a lot of work, was essentially in details. So I would argue that the same is true for many codes, that the overall structure can be determined in a relatively straightforward way, but after that you have to do a lot of work. So the overall structure of the HACC code is that there's a universal top layer, and I'll give you a bit more details about how the universal top layer works. And there are plug-in node-level components. And so the idea is that the overall top layer you don't fool around with. You've written it once. It's a nice framework. It does a lot of things. But when you need to go from one machine to another, there are plug-in modules that basically go in and out as you switch from one machine to the other. And you follow the standard rules of minimizing the data structure complexity and minimizing data motion in building these things. And that is a central message here. Data structure complexity is a major killer, and I think it's important for people for doing supercomputing to avoid that. So the programming model that we use is, and honestly, I'm not so concerned about the overall language. I mean, you want to write in Fortran, that's fine. It's not a big deal. But we use C++ MPI for the universal top layer, and X, where X is whatever you want for the lower level. So it's OpenMP, for example, on the IBM Blue Gene Q. It's a cell SDK on the cells. It was OpenCL originally on the GPUs, but now we have also CUDA version, and obviously CUDA is here. And there could be something else, whatever the next generation machine wants. So the important thing here is that there is an algorithm co-design. We are not actually co-designing to the hardware, because obviously we cannot control the hardware, but we can control the algorithm. So what we did was we decided to co-design the algorithms against what we knew were the possible hardware futures. So the code has multiple algorithm options. It has a lot of stress on accuracy and on low memory overhead. And one of the other things is that we wanted to run on new machines as soon as they became available in order to be able to tune the code and change things around as quickly as we could. This meant that we could not rely on any external libraries because those take time and they're hard to rely on. So a lot of the stuff, there's only one or two things like MPI that we assume exist, and occasionally we will use FFTW, but we don't have to. So pretty much everything in the simulation path is library free. So this allows us the luxury of running on new architectures as soon as they're available. And I think this is very important, and people should think about doing that to the extent they can. In many cases, this is impossible. Your code is too complex. You're using too many libraries. You will not be able to do this. But if you can, it's an important thing to think about. We also have a major analysis framework that goes along with the code, but I will not talk about that too much. One of the important things about dealing with multiple algorithms is something to worry about, is that people often concern themselves with verifiability, meaning that I run the code and then I change on a new computer. I want bitwise the same answer. And with our approach, that is very, very difficult. You are not going to get that, so which means that you have to have a very, very good idea of error controls within your code. Are you willing to tolerate errors of a certain level? And as long as you have the codes, different versions of the codes agreeing within that level, then you're fine. Okay, so now let me say a few words about the HACC overall structure. So the universal layer is a 3D domain decomposition, and it uses a trick called particle replication at the boundaries. And this is a very important trick because it actually allows us to reduce, and I don't have time to explain in detail how it works, but it allows us to reduce the amount of communication. Within each of the domains, there are subdomains, and the subdomains are handled by what we call the HACC nodal layer. And that's where we actually have the part that depends on the architecture. So there's a long-range solver, which is solved by by our own custom-written FFT, and then there's a short-range solver which depends on the machine that you're using. And it uses what I call particle-particle method. It uses a tree-based data structure to handle that, and it also uses chaining meshes and so forth. But these are technical details, and I don't want to spend time on them. But the important thing is that you can do all of that, and they're explained in the previous slide and in this current one. So the reason all of this particular slide is somewhat dense, and I'm not going to actually talk too much about it, but everything that I'm saying in the slides that follow, kind of follow from this particular structure. So the code was written from scratch. It has all these features that are actually presented in this slide. So let me move on and go on to the next slide. So just to give you two very different examples on which our code runs. So one of them is the IBM Blue Gene Q, which is a kind of uniform, very large machine. And it's based on the BQC chip, which has 16 cores, and it has 205 G-flops. So very similar if you keep in mind the Roadrunner is 200 G-flops per cell. It has 16 gigabytes of RAM and 32 megabytes of L2 cache. Now, and then, it has a 5D torus network and so on. So in this particular case, we have a two-tiered programming model. We use MPI on the overlayer of the code, and we use OpenMP. And use of vector intrinsics is essential for getting performance. I mean, details of this performance and how we achieved it are given in different papers, and you can go look them up. But the important thing is that it's a machine that is, kind of a precursor to the next generation systems that are in the many core class. So on this machine, when you run our code, you get extremely high performance. And this figure is showing you how the scaling of the code works. So this is a benchmark that we ran actually on Sequoia, which is a machine at Lawrence Livermore Lab. But we also run similar benchmarks on Mira, which is a machine at Argonne. So this has the biggest cosmology simulation ever done with a 3.6 trillion particle benchmark. And you can see the code scales perfectly. And it has run up to 1.5 million cores with 6.3 million way concurrency if you include the threading. So in principle, what this tells you is that a very complicated piece of computation can be done on these large systems with perfect scaling. Not only is the scaling perfect, but one thing I want to remind people is that it is run at very high efficiency. So this code ran at almost 70% of peak on this machine and got 14 petaflops. And it had 90% parallel efficiency. So the point is that you can write a code that is portable in some sense, because it has this node level optimizations which can be plugged in and out, and you can get very high levels of performance. So that was an example on the BGQ. So now let's go on to another example, which is quite different, and this is the Cray XK7, and this is a machine called Titan at Oak Ridge. So here you have a difference. You see now, that you have 32 GB on host side and 6 GB on the GPU. So again, this is quite different from Roadrunner's 16 GB on the processor side and 16 GB on the cell side. So when we were writing the code for Roadrunner, we did something that was interesting. We put all the particle information on the cell side, the accelerator side, and all the grid information, because our code is a hybrid code, has both grid and particle information. The grid information stayed on the side of the opterons because most of the computation was done on the particle side. However, you cannot do that on the XK7 because all the memory is sitting on the host side. So therefore, you have to think about how you're going to stream the data to the GPU. And the PCIe, as in many of these accelerated systems, turns out to be a key bottleneck. And so once again, you have to be very careful about how you interleave the communication and the computation. That's a key point in this. There's absolutely no point in a system that is so out of balance between the host and the GPU to share work between the CPU and the GPU, because your performance gains will be minimal. The GPU must dominate. So people should be very careful about this. If you're going to have an accelerated system where the potential for improvement in performance is something like a factor of 10 or so, and you're only getting a factor of 2, something's wrong. You've kind of wasted your time. So that's, I think, something that people should keep in mind. And there are some strategies for success I've written here, but they're very similar to what I'd said earlier, so I won't say too much about it. The following slide just talks a little bit about, how exactly this pushing the data was done and so on. And in fact, on a slightly older slide, we have improved this. And it's a bit technical, and I know that I'm a bit short on time, so I won't talk about this too much. Anyone has any question about this, they can certainly ask. And I think I'll move on at this point just to show you the performance that we got on Titan. And on Titan, we have continuously improved our code, we've improved load balancing and so on. And this figure kind of shows over a period of time how things improve. And here I also gave you some strong scaling information on this system. But again, you have pretty much ideal scaling, and you can get very high levels of performance. So, we can get, for the kernel runs at 1.6 teraflops per node, for example, and the 3PM kernel runs at something like 21 petaflops. And we can get extremely good, strong scaling results at the same time. So that convinces us that, the strategy that we are using is actually a very good strategy for future machines as well, because it runs so well on the many core and it runs really well on the GPUs as well. So I think this is a good point to sort of good time to summarize everything. And so the basic point I want everyone to get away with, and of course some of you are experts, I'm sure, and and this talk is really not meant for all the experts out there, but it's extremely important to put a lot of thought into your design of a flexible code infrastructure. You should minimize absolutely the number of computational hotspots, because that's going to be essential. Because if you have too many computational hotspots in your code, you're going to lose performance because of the whack-a-mole problem. And the second thing is that it's going to be hard to deal with so many hotspots. So if you have to write a code and you say, well, I'm going to lose a factor of, say, 20-30%, but I end up reducing the number of computational hotspots, I would definitely do that. Because each of them you can then kind of deal with individually in a better way. It's also important to explore multiple algorithmic ideas. And for this, domain science expertise is very, very essential. Because sometimes what happens is, let's say I give you an n-body problem and I say, please solve this. Somebody who doesn't know that I only want an approximate answer may come up with a fancy exact algorithm, but I don't need it. And an approximate algorithm would have been orders of magnitude faster and would have gotten me the answer that I need. So exploit the domain science expertise to think about different algorithmic ideas. One thing I wanted to mention, and I may say that over and over again, is that machines are very out of balance. So focusing only on the lowest level compute-intensive kernel can be a mistake. So if I really optimize on chip, I may find it didn't do me any good. So you have to really, so don't do this lowest level optimization first. Think at all. Have to cover all levels, but think on the highest level first and then go down. So, and as I try to say that, at least for our code, one possible solution is this overarching universal layer with architecture-dependent plug-in modules. And this has also implications for productivity, because you can bring in people who are experts on a particular architecture. Now they don't have to know what the heck the code is doing the rest of the time. You just tell them, here is the module, please, it does this, it's designed for your machine, but can you optimize that? So this helps a lot. One of the key issues to understand in running these very extreme scale problems is data motion is a killer. And so minimizing the data motion, looking to hide communication latency with computation, always is going to be very, very crucial. The other thing is that all of these codes need to be changed on fast timescales, because the architecture is changing on relatively fast timescales. So whatever you can do to keep that changeability, make that changeability easy, I think that's extremely important. Finally, as the science outputs become more and more complex, it used to be that supercomputers ran a large amount of code and the answer was a single picture or a single graph or even sometimes a single number. That's not true anymore. As the science outputs are becoming more complex, the output itself is huge. From some of our simulations, we are generating something like 4 terabytes for a single snapshot, and we may have 100 snapshots. That's 400 terabytes from a single run. And so just analyzing that takes a significant fraction of computational time. So one of the things that the community has to deal with in the future is also the fact that the computers are data generation engines in their own right, and how do you deal with all of this data? So I'll leave you with that and look forward to your questions. Thank you.
Thank you, Salman, for the interesting talk. Let's move on to some questions that have come in. So one question is, what if there is no core kernel in the code? Some multiphysics codes have 6% of the work in the most compute-intensive kernel, and then the percentage drops off rapidly for other top-used kernels in the code.
Yeah, so I think this is a problem, right? So if you have a situation where very small, where you have a fractional piece like that, then you're almost almost no way to do anything. So a lot of the multi-physics codes, and this is a very good point that has been brought up, simply cannot be optimized beyond a certain point because you're dominated by lots of little things that you have to do. And so there, I would argue that your issue may be somewhat different, meaning that you're happy to live with something like 5% of peak, but your main issue may be portability. So you may still want to think about how to redesign your code in such a way that you can port very efficiently across the architectures. And even though you're not going to get extreme performance on any given architecture. I should say that currently this is true of most codes running on supercomputers. If you go and ask how efficient are they, the typical code is running at less than 5%, maybe 5% of peak. And this is going to get worse, right? As the machine becomes harder to program for, this is going to drop even further to less than 1%. So all of these are important questions, and I don't think there's a one single answer to this.
Okay. Another question is on the programming issue. What is your opinion on future languages and runtimes such as Chapel or Legion? Do you think they will help solve some of the programming issues, and are they alternatives to the MPI plus X models that you think applications could use?
So in principle, the answer is yes. So in other words, I've looked at Chapel. I think it's a beautiful language, and there are other things have. Let me give you an example, right? In the past there was something called high performance Fortran, and for many things, HPF was fantastic. It was very easy to program. You could write a code in one weekend, or connection machine Fortran that ran on the CM5, which had a very, very good, library for stuff, the CMSSL. And literally on one weekend, you could write a super powerful code. So I'm all for high-level languages that improve my productivity and get me to do things very quickly. So to the extent that such a thing actually exists, I would say it'd be fantastic. But as a practical matter, building something like this now for a multiple architectures is going to be super difficult. So that's what I meant by defensive programming. So if I'm running a code team, I can't wait for these languages to exist. I have to solve my problems today. So for today, I would say I'm sorry, but there is no alternative to MPI plus X. And if some later time an alternative appears, great, but it's not true right now.
Okay. Another question that has come in is for the codes that ran on Titan and the one that ran on the Blue Gene, how much was the difference in the code, and how much does that affect in terms of code maintenance? If you have a lot of difference in codes, it's harder to maintain. So
yes,
how much do codes differ?
So that's actually a very, very good point, and this is something that has been something that we obviously worried about, right? So the idea is that the overall universal part of the code that we have, that never changes. So that's, clearly it has to have minor, very minor changes when you go from one machine to the other, but that is essentially fixed. That evolves, independently of the machine architectures to some degree. But the short range force solver is definitely different for particular applications, and so that does lead to an issue, which is you have one person who's handling one thing, another person's handling something else. So maintainability in this approach is definitely something that is somewhat of a challenge, right? No question about that. So the problem is that we could give up performance for maintainability. And in this particular case, because we needed the performance, we didn't do it. And as long as what people call swim lanes, which is the number of architecture choices, is a few. Let us say the next generation of machines, choices for us, at least in the US, are many core and GPU, and that's only 2. So 2 we can easily handle. But if someone came to us and said there's going to be 6 different architectures, okay, that's going to be painful. But 2 or 3, our code is fine with.
Okay. Another question is, what does HACC stand for? And have you tried running it on the Intel Xeon Phi? And if so, how did you run it, or what changes did you need to make to run it on the Phi?
Okay, so it just stands for Hardware/Hybrid Accelerated Cosmology Code. That's what HACC stands for. And yes, it's been run on the Intel Xeon Phi from very early times. The reason we didn't run it on a very large system was that we didn't have access to a large Intel Xeon system until very recently. We are part of the NERSC project, which is basically running early science runs on Intel Xeons. And I would say that the change from the BGQ kernel to the Intel Xeon is not much. So, I would argue that days of work are all that are needed. In fact, has been done already. In fact, Yeah. So it's very straightforward. I mean, obviously, some very smart person has to do this, but it's relatively straightforward.
Okay. Another question is, what about resilience or fault tolerance? And have you felt the need to add any features to detect errors or failures or recovery from failure?
Yeah, so that's actually a very interesting question, and we have been, in fact, thinking about this quite a bit because obviously we worry about errors and resilience, and with Frank at Argonne Fellow, we've been looking at certain things. So basically, there's two things that worry us, right? One is catastrophic failures, which honestly don't worry us that much because, well, if something crashes, then you can figure out what went wrong. But the more worrying thing, aside from bugs, which happen all the time, are silent errors of a certain kind that are hard to detect. So we have a number of error detectors that we are working on, which are based on the fact that the trajectories of the particles in our simulation are relatively smooth. So if the particle does something weird, we want to know why it did that. The other nice thing about our code is that essentially it's a dynamical Monte Carlo code. So intrinsically it's resistant to a lot of bad things that can happen. You're running trillions of particles, a particle here, a particle there. You don't really worry about it too much because the answer is it's just a minor effect in the statistics on the final result. But there are enough hooks in the code for us to do verification and validation of the results. And we have been doing things like injecting errors and seeing how well they show up and so on. So I think in the future, especially for silent error detection, codes will have to be instrumented. And I think that's an important thing to do. Moreover, codes will have to be written in a such way that they're also defended against code modules that are misbehaving. Because sometimes what happens is your code can run perfectly fine, but let's say there's an analysis module that is doing something weird, and it's inessential. So during the run, you just say, forget it. I don't worry about that. There should be a way to defend your code from that. So we are thinking about all of these things.
Okay. Another question is, can you comment on how you think I/O burst buffers could improve the I/O performance of workflows in the future, and whether you think a programming model for burst buffers is needed or not?
I see. That's an interesting question. I'm not an expert on burst buffers, but I mean, so beyond knowing, how exactly they will work, so I think certainly having burst buffers to improve I/O performance is very, very important, right? I think that is definitely a very good thing. We have been thinking more along the lines of next step beyond burst buffers, meaning NVRAM, local NVRAM, to do a lot of interesting things. And so a programming model that actually allows us, so let me not just say burst buffers, but allows us to seamlessly, tackle NVRAM would, I think, be quite useful. So something that is a localized programming model that enables you to deal with NVRAM as another quiver in your memory space, I think would be quite useful, and I/O as well. Something that allows you to use it easily would be quite helpful.
Okay. Another question is, what is the reproducibility criteria that you use to check that port of your application from one machine to another is generating the same result, or?
Oh yeah. So yes. So that's a very, very important question, right? Because when we run across two different machines, we are actually running two completely different algorithms. So in effect, we are running two different codes. But we are solving the same problem with two different codes, which have different error properties. So this means that from the science perspective, we must know if for certain error metrics, how well our codes are doing. So we have several error metrics for observable quantities that we run on our code, things like power spectra, correlation functions, various things. And for each of them, we have a statement that over a certain dynamic range, the agreement must be, better than 0.1% or whatever it is. And as long as it's that, then we say, okay, great, these things are working. And there are other tests that we do that are simpler and more along the lines of, is sanity checks. So there are sanity checks and there are accuracy checks. And, the code has to satisfy both of them.
And what changes do you anticipate you'll need to make for the code to scale to exascale systems?
So, I don't want to sound overconfident at this point, but I don't see having to make too many changes because, our code was a benchmark code for the Coral procurement at Argonne and Oak Ridge and Livermore, where, vendors and us and other people already checked the code out on systems or potentially check the code out on systems which are going to be running at, in the low hundreds of petaflop. So to go to exascale is another factor of 5. And there's nothing I see that stops us from getting that factor of 5 by the approach that we have now. So my view is that as far as exascale is concerned, meaning a few exaflop, I don't see any big issues. The issues that I do see coming up, so for the gravity only part, I don't see a big issue. The issue I see coming up is as we add more physics. So we have a new hydro solver that we'll be adding to do gas physics. Then those are the places where we will need to worry about how well the code does. But I'm pretty optimistic. I don't see, any showstoppers up to the few exaflop.
Okay. Another question is, what performance analysis tools do you find useful for MPI plus X codes?
So this completely depends on what the machine makes it available. So honestly, our first job here is to do our science. So, and we don't actually worry too much about instrumenting the code for performance. So usually what happens is when we are running on a new machine, we are careful and make sure that the performance-intensive kernels are running as appropriate. So, so we used on the BGQ, HBM, there was a monitor that was written. And we had a hell of a time, I have to admit, on Titan because we couldn't get, a good performance number. And so I think it would be nice to have flop counters that are easily accessible. But I don't think this is the first thing to worry about for somebody who's writing an extreme scalable code, because these are things that you worry about when you're at the final level of tuning the code. Really, what level of performance am I getting? Do I really need to worry about whether it's 50% or 60% of what I could possibly get? So I would say that some effort in these directions is good, but it's not going to be, it's not going to be a make or break situation.
Okay, I'm afraid we've run out of time today, so I'd like to thank Salman again for his informative presentation and insightful answers to the many questions. And a special thanks to all of you for taking the time to attend and participate today. This webinar was recorded and will be available online in a few days at learning.acm.org/webinar. You can find announcements on upcoming webinars and other ACM activities at learning.acm.org and acm.org. Also, please fill out the quick survey where you can suggest future topics or speakers, which you can see on the screen now. This is Rajiv Thakur saying goodbye for now. Thanks again for joining us, and hope you will join us again in the future.